So in order to show that the derivative of e to the x is in fact e to the x, we need to first go to the bank. So on example 12a, let's say that you had $1 to put into an account for a year, and the interest rate was a very reasonable 100%. 100% interest. Okay, all right, yeah, that's going to happen. How much money would you have in the account if the interest was compounded once? Well, okay, remember what compound interest is? You accumulate money for, actually you put the money in the bank uses your money, and they pay you for it. That's called interest. And then compound interest is when they take that interest and they put it back into your account so that the next time they compute the interest, you have more in your account. So then it starts to accumulate faster. Okay, so we want to know what happens if it's compounded once, twice. Does it continue to grow as n is the number of times that you compound it? Does it continue to get bigger and bigger infinitely? Do you remember what the compound interest formula is? It looks like this. The amount in your account is equal to P, that's your principal, that's your initial investment, times 1 plus R over N. R is your interest rate, written as a decimal. N is the number of times you compound it. All of that raised to the nt power. Again, n number of times you compound it. T is how long you're going to keep it in the bank, how many years. Okay, so we want to know that if we just keep compounding this interest, does it just blow up and get infinitely big? That's what this question is trying to get to. So here, let's come over here and let's rewrite our equation specifically. Hey, this is purple. This gets purple. How about this shade? Okay. So this amount in our account is going to be equal to, our principal here is we have $1. So we're going to put in $1 in the bank. Okay. And then I'm going to multiply that times 1 plus, our interest rate is 100%, written as a decimal number is just the number 1, over the number of times I compound it, and it'll just be n, raised to the nt power. And our t is just 1 year. We're only going to put this thing in the money, or in the money? Yeah, into the account for a year. I think that says that. Yeah, for a year. If you have 100% interest, why are you only putting it in there for a year? That's my question. All right, so this is going to be to the nth power. Of course, we don't need that extra 1 that's on the outside there. That's just, redundant. So let's see what we would get if we compound this just one time. This would be equal to 1 plus 1 over 1 raised to the first power. Well, that's just 2 raised to the first power, which is 2. I have $2. I've just doubled my money, 100%. That makes sense, right? $2. All right, then let's say that we compound it twice. So compounding it twice, that's semi-annually. 1 plus 1 over 2 raised to the second power. Well, this is 1.5, right? Squared, and that's, I think it's $2.25. Let's see, with some other things that you sometimes see interest rate compounded, 4, as in quarterly. So let's try quarterly. This would be 1 plus 1 over 4 to the 4th power, that's 1.25 to the 4th power, is equal to, something. All right, it's time to break out the calculator. Let's get Desmos up in here, and let's type in our function as an a for amount. That makes sense. We'll make it a of x, since I'm not going to use an n here for my independent variable, is equal to, and I don't have to write the 1, so it's just parentheses 1 plus 1 divided by x, and then we're going to arrow out and then raise all of that to the x power. Okay, that's an interesting graph, but we're working with purple, so we're going to change that to purple. Okay, and then let's go ahead and make a table of values. So we've already done a couple of these, like we did 2 for, 1, as in it was just compounded at the end. And then let's do 2 semi-annually, and then quarterly. This is the one that I was just working on, but I didn't put it into the calculator, but Desmos going to do that for me. 2.44 blah, blah, blah. But as far as the amount in my count, you can only have that 44 cents, right? Okay. And then let's see what else. We could do monthly. So for 12, oh, look, it went up some more. But how much is it? Like the first one, of course, it went up by 25 cents. Did it continue to go up by more and more? Or is it slowing down? We'll take a look at the graph there. Doesn't it look like it might be slowing down and approaching a particular number? I wonder what it is. Okay, so let's say that we do it every single day. We compound daily, 365. Okay. Well, it looks like we went up by maybe 10 cents. All right, well, let's see if we can get it a little bit better. Let's see, instead of daily, what about hourly? So that would be 365 that we're going to multiply times 24, which is 8,760 hours. Almost the same number. And if you look at the 8 there, it's 2.718. That 1 would actually round up to 2, so you have $2.72. So really, you just earned one more penny? Okay, so let's maybe do not hourly, but every single minute. So if I multiply that by 6, I get 525,600. Well, you can see that the 2.718, all of that stays the same, but we've got just slightly bigger numbers after that. Okay, so what about, every second? Secondly? Every second. All right, so just multiply that by 60 again, and you get 31,536,000. Well, what do you know? It seems like now the 2 is not changing, it's stuck in place, and then we get an 8 after that. What's happening? What is happening? It looks like it is approaching a particular number, and do you know what that number is? 2.718, blah, 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 blah. It is this number here. So I'm going to come right down here to this next one, and I'm just going to go y equals, and I have to go over to the QWERTY keyboard and then hit the E. And then maybe change its color, because why do I want the same exact color for that? And maybe make it dashed or something like that. So now looking at this graph, I can see that it's getting closer and closer to that. A horizontal asymptote. I wonder if we can express all of that as a limit. Well, here, let's go back to the slideshow here. And we were able to, we basically made this table of values. I compound it once, I get $2, compound it twice, $2.25, but we increased by 25 cents, not bad. If I compound it quarterly, I only go up by 19 cents. It's starting to slow down. I do it every single month. Now I've just gone up 17 cents, slowing down by a little bit more. Do it every single day. Now I've gone up 10 cents. But right after this, I've hit a brick wall. I got 1 penny, and I can never, ever, ever get any more than that. And that number is the number E. Well, it's rounded right there. And on this next one, we're wanting to use graphical and numerical methods to approximate this limit. And that's exactly what we were doing whenever we were plugging numbers into that table and looking at that graph. So the limit as x goes to infinity of 1 over 1 plus x to the x is equal to, well, here's all of these numbers populated, 10, 10 to the second, 10 to the third, and so on. And you can see that very, very quickly, right here, the numbers get stuck. You're going to get more and more decimals after this, because this is a transcendental, irrational number, super special number. This is the number E. As a matter of fact, this is the limit definition of E. And we could show that this limit actually, we could derive this limit and show that it's E, but we need more calculus to do it. So for right now, we're going to understand that the limit as x approaches infinity of 1 plus 1 over x, all of that raised to the x power, is equal to E.